That's good. Okay, so it's my pleasure to introduce Mirco Tribastone, who will talk about maximal aggregation for polynomial differential equations.
Okay, so thank you very much for the invitation, and thank you everybody for coming. So yes, I'm Mirco. I'm coming from Lucca, from Italy, from the School of Advanced Studies. It's a PhD school, essentially. And what I'm talking about today, and I'm a computer scientist, like all of my colleagues that are essentially the co-authors of a series of papers that have been looking at the problem of reducing systems of differential equations of different kinds. That's okay. So I'm very grateful for them for all this work, and I will try to show you today essentially the culmination of our work about reductions of systems of polynomial differential equations. Okay. So what is the motivation? And our original motivation for studying systems of polynomial differential equations was essentially coming from a thesis biology or biochemistry. There is a lot of work in particular in computer science about computational thesis biology, which is about trying to define computational and mechanistic models of biological systems. And using methods from computer science, for example, languages and so on.
What is a mechanistic model?
Mechanistic means that you have a model that describes the mechanics of how things interact in a living set, for example. So essentially you come up with a huge list of reactions that are biochemical reactions that essentially describe, I will give you some example later, essentially describe how somehow information is processed in living cells. I will give you some examples later to try to understand what we get. But essentially, if you think of a kind of biochemical model, it can look like something like that, where you have many nodes, and each of these nodes can be some complex, a protein or RNA or DNA, that essentially interacts with other pieces of a living cell in order to do some process, in order to do something, like inhibiting, activating, and so on and so forth. So you have nodes, and then you have edges that are essentially saying what happens when a node interacts with another node on the rest of the system. So if the high concentration of some protein inhibits or activates other proteins in the cell. You can measure these things, and you can assume that there is some kind of interaction that evolves according to systems of differential equations, and what you end up with is a huge system of nonlinear differential equations, where each equation describes the evolution over time of the concentration of each specific node in your system. So the larger the graph, the larger will be the system of differential equations. The same thing, of course, is very well known in engineering, where you have physical laws that describe the evolution of physical processes like current, voltage, and so on. And then you have one equation for each node, for example, of some electrical circuit. And because of that, we need somehow reduction. We call it reduction or abstraction methods that are essentially needed to compress the model itself. And that's needed for two reasons. So one reason is that we want to be able to analyze the systems faster. In many cases, those system differential equations do not enjoy closed form analytical expressions. So all you're left with is a kind of numerical simulation. And of course, numerical simulation will be, the cost of the numerical simulation will be proportional to the complexity of the system in terms of number of variables and in terms of a kind of complexity of computing the derivatives at each point in time. But you can also look at abstraction for a different reason. Abstraction is somehow also needed in order to gain physical intelligibility of your model. By that I mean that when your model is so complex, you don't really understand what are the main drivers of the most important dynamics of your system. If you have a smaller model, this can be easier to understand. And I will give you some example of our techniques applied in particular to biology, where essentially we could reduce the complexity of our system, trying to understand what are the things that were invariant, and the things instead that really determine the behavior, the dynamics of the models. So in this talk here, I will be working with polynomial differential equations, where essentially it's the class of differential equations where the derivatives are multivariate polynomials over the system variables. So they are, of course, very popular, in particular in systems biology, in biology or in chemistry. The law of mass action states that the rate at which reactions happen is proportional to the product of the concentration of agents. So there we have a product, which is in many cases, which is essentially can be encoded as a polynomial system of differential equations. But of course, they can also encode other nonlinearities, like trigonometric functions, rational expressions, exponential functions. And these can be useful, for example, in biochemistry when you want to model other kinetics than mass action, for example, Hill mechanism and so on. And you do it in a very simple way, essentially at the cost of extending the number of variables in your system by using auxiliary variables. So here is just an example to try to convince that polynomial differential equations are not so restrictive. So if you have differential equations which got a sinusoidal form here, well, then you do a change of variable, you consider its derivative, and you end up with an expanded polynomial system, in this case linear system of differential equations. And of course there are ways of doing it kind of automatically. For example, there is this algorithm that given a description, syntactic description of system of differential equations, it gives you the resulting polynomial encoding of that.
I have a question.
Yes.
You didn't put the initial conditions here.
Yeah.
How would they transform? Would they also
they need to be consistent.
But would they also transform polynomially? So is it actually an equivalent question?
Yeah.
Or it's not an equivalent
It
question?
is equivalent. Because this is equivalent to that so long as z of 0 is equal to the sinus x of 0 and w of 0 is equal to the cosinus of x of 0. So the transformation is to be consistent such that this holds also for the initial condition. For whatever x of 0, w 0 has to be equal to the cosinus of x of 0. And for any x of 0, which is given here, z of 0 has to be equal to the sinus of x of 0. Otherwise, of course, that doesn't make sense. So the bottom line of this slide is that from now on we talk about polynomial differential equations, having in mind that in many cases they are not restrictive as a class of systems. So, okay, this is something that is, of course, known to you. I'm just using that as a reminder of the notation that I'm using. And essentially what we have, well, the input to our problem is a system of differential equations where those f's are polynomials over the variables x1, xn. And we assume that we don't have an analytical solution, closed form solution, so essentially we end up with some kind of numerical solution. And this is essentially, this is clear, this is obvious, but this is essentially what triggered our idea of applying the methods for computer science and from, if you like, discrete mathematics to the problem of solving aggregating system of differential equations. Because you can think of this iteration here as a kind of a small computer program, which given the current state of your variables or your memory, it gives you which is the update on those variables at the next time step. And then, if you think in terms of with this idea, you can try to imagine to be able to apply techniques of minimization of programs to this kind of setting. You have a question?
So in the ODE dynamical system here, you would not allow, let's say, the derivative of xi to be squared or cubed?
Yes, we do allow.
You do allow, but
Yes.
the system, where is it expressed then?
I'm saying that f is a multivariate polynomial.
But it doesn't involve the derivative of xi, do
No, so he's asking, what if you have a constraint, polynomial constraint on the derivatives?
Yeah.
Like x1 dot squared plus x2 dot cubed is equal to something.
Oh, you mean a differential algebraic system?
Yeah,
Yes.
right.
Okay, I'll come back to that. I'm actually going to Miami to present results extended to differential algebraic equations. At the moment, we have polynomial ordinary differential equations. So
It's still all, but right now this is dynamical and
So, William,
autonomous.
by ODEs, actually, many people mean a system of this form.
I understand.
So linear in the highest
Okay, fine.
derivatives.
yes,
Fine.
yes. So left-hand side, vector of derivatives, right-hand side, multivariate polynomials over the variables x1, x7.
Right.
Okay? Then I'll come back to the point. Actually, I'm not presenting it, but we have some extensions to what we call differential algebraic equations, where this is multiplied by a matrix, which can be singular and so on, and can be general, so you can consider different kind of constraints. Okay? Other questions so far? So essentially, yeah, the problem is that the actual solution depends on the number of variables, but also on how complex those functions are for the computation. So our approach is that of a model reduction. So what do we mean by model reduction? Model reduction can take many different implementations, if you like, depending on the kind of discipline that looks at that problem. Sorry. So for us, model reduction takes a very specific form where essentially we are given an original system, and then somehow we want to find a reduced system with some constraints on that. So the first constraint is, which is our hope, is that m, the number of variables in the reduced system, is much smaller than n, because otherwise it's not a sensible reduction. And then what I'm presenting today is an approach that is exact, is observable preserving, and it is automatic. So let me try to understand what I mean by exactness. Of course, here, assuming that m is smaller than n, I am projecting onto a lower dimensional space, so I'm losing something. What I'm saying by exactness is that what I'm not losing is can be exactly related to the original system. Observable preserving, we don't have any notion of observation here. We're talking with Gleb this morning about similar things in control systems. Here, this is not a control system. We don't have an observational map or anything. But clearly, many experiments in real life, when you use differential equations for modeling, these are the state variables, but we are not really interested in the behavior of all state variables. We are interested in behavior of some representative state variables. Those could be, for example, some linear combination of the original one, or it can be just a subset of them. What we would like to do is to find a technique that essentially preserves the things that you're interested in and tries to aggregate all the rest, which is important for the dynamics, but is not of direct concern to the model. And of course, we want that to be completely automatic. So we want to develop an algorithm, hopefully as efficient as possible, such that given a specification like that, it gives you a reduction like that. And in particular, what we are doing is that we developed an algorithm that gives you the maximal possible reduction according to some specified notion of reduction that I will try to explain in the next slides. Okay? So, our notion of reduction is essentially called the lumping, which is a very specific notion of reduction, which can be traced back to, well, this is a review 20 years ago of already a lot of work done in particular in chemistry. And essentially, it's about finding a partition of variables, of differential equation variables, such that each partition block can be associated with a single equation in the reduced system. So in our case, what we call the lumped ODE system somehow preserves the original dynamics according to two notions that I will try to explain are complementary to each other. So we have one notion which is called forward lumping. And forward lumping means that the variables in each block will preserve the sums of the solutions of the variables in each block. So if we have two variables, x1 and x2, that are lumped together into a single macro variable that we call y, then we know that y is equal to x1 plus x2. And we call it forward for a reason that I will explain in a second. We also have the backward lumping that essentially identifies variables that have the same solution in each block. So if x1 and x2 are lumped in the same block, so they are equivalent, we know that x1 and x2 are equal at all time points. And of course, this is a technique that is essentially complementary to other techniques that simply, for example, look at a fast, slow decomposition of time scales in differential equations. other abstraction techniques. I will give you references in the papers that are referenced at the end of the slides. Yes. Please.
You intended to give an example, right?
Yes, of course.
Okay, great.
Yeah, sure. So I will show you forward lumping as a simple example. It's a bit contrived. There are lots of equations just to show more than one equation. But this is a polynomial system of differential equations in the sense that we discussed before. 5 variables and some non-linearities, which are products. This could be, for example, coming from a description as a kind of chemical reaction network, for example. So what we observe is that if we assume that we know already that x1 and x2 are equivalent, they can be put in the same block, and x4 and x5 are also equivalent, we can define a reduced system that works on those macro variables. And this reduced system enjoys the property that y1 of t is equal to x1 of t plus x2 of t for all time points, assuming, of course, that you initialize the initial condition y1 of 0 such that it's the sum of the initial conditions of x1 of 0 and x2 of 0. This is clear from here. You see it already. If you do the sum of these two equations, the derivative is linear, this goes away, and then you can rewrite the right-hand sides in terms of sums x1 plus x2 and x4 plus x5, because these coefficients are the same, so you can factor them out. The same you can do for y3, and y2 stands on its own. So if you, in your model, if you are happy with just observing x3, you have a reduced model such that x3, the behavior of x3 is preserved, and then you are lumping the behavior of x1, x2, and x4 and x5. But you keep the exact sum. And of course, okay, here is a graphical representation of what is happening. If I plot x1 plus x2, well, that's equivalent to y1 here, but that's good, right?
And so you earlier mentioned that there are some variables that are interesting and non-interesting.
Yeah.
Is this incorporated into blood take itself?
Not at the moment. It will be incorporated into the algorithm. I'll come back to that in a couple of slides, 2 or 3 slides. At the moment, here, somehow by magic, I'm telling you that this is an equivalence according to a forward lumping. But this you can kind of guess from manual inspection. What we want to do is to find an algorithm that gives us those partitions automatically. So at the moment I'm saying what the lumping is, and then I will tell you how the lumping is computed.
And what would be a reason just to consider sums and not something more general, some linear combinations?
Excellent questions. Well, so this was already quite difficult. The problem is that what we are doing technically in order to find the equivalent, to find those lumpings, is essentially to translate this problem into the problem of finding the largest equivalence over some structure. Now, so what we are really finding is just equivalence classes of variables. So we are finding that the x1 is equivalent to x2 and x4 is equivalent to x5. And then this equivalence implies preservation of dynamics in terms of sums. If you are allowing, if you want to be more general and you want to allow also a linear combination of that, then the equivalence becomes a little bit more tricky, because not only do you have to choose the variables that are equivalent, but also you have to find somehow the optimal coefficients of the linear combination. And so far we have failed to extend our results. We have not looked out into the problem, but we have failed to extend the results to the arbitrary linear combinations. Of course, you can also have notions of nonlinear lumping, where essentially you are allowed to preserve nonlinear expressions of the variables, and there are some examples in the literature, in the chemistry literature. But we were not able to find an algorithmic approach, an algorithmic solution to finding those lumpings automatically. So for the moment, we restrict to essentially equivalence classes of variables, equivalences between variables.
But maybe this kind of substitutions is already good enough for many systems.
Yes. And I will try also to give you the physical intuition why it is good enough later on. For some classes of systems, of course. Okay? Other questions? So now I will give you also the example of backward lumping, where essentially identifies variables that have equal solution at all time points. So essentially the second condition is that they need to start with equal initial conditions. So if this is the original system with three variables, what we observe is that if x1 is equal to x1 of 0 is equal to x2 of 0, then the derivatives will be equivalent, which means that the solutions will be equivalent at all time points. So what I'm doing is that under this assumption here, I can say that y1 is x1 and x2. So essentially I replace one of the two, or replace all of them by y1, and I get here this equation. I do the same also on x3, and I get this equation here. And now I have a reduced system that mimics the original one under that assumption. Notice that in the case of forward lumping, we don't have that assumption because we just sum across all the initial conditions of the variables that are equivalent. Here, we need to be careful about the initial conditions of the variables that are equivalent in the reduced system. Okay?
Is it correct that if some partition is good for backward lumping, then it is also good for forward? So
No.
it's sort of special case.
They're not comparable.
Okay.
So this is a forward equivalence that does not imply backward. It is forward because I can express the sum of the two in terms of x1 plus x2, but it's not backward because this has got a drift, which is not here. So even if they are equal at time 0, of course, they will have different solutions. And here is a backward that is not implying forward. Of course, if you start with same initial conditions, those solutions will be the same. But it's all forward because you cannot write the product in terms of the sums of x1 and x2. Okay?
Right. Okay, thank you.
So where are those names coming from? Why am I calling them forward and backward? Essentially, the name comes from lumping in continuous time Markov chains. And are you familiar with lumping of Markov chains at all? Okay, so I will try to explain what it is. Are you familiar with Markov chains? More or less. I will try to explain what it is.
There was no answer.
Huh?
There was quite no answer.
So what is it? A Markov chain is a stochastic process that essentially satisfies the Markov process, the Markov condition, such that in order to understand the future evolution, the stochastic evolution, you just need to know about the current state where you are. Of course, I'm not going to go into the details of that, but trust me that you can express a Markov chain, a stochastic process, in terms of a graph like this. So this graph has got three states, which are the different states in which the Markov process can be. So at any point in time, you have a probability distribution over those three states. And you can try to understand what is the probability of being in this state, in that state, or in that state at any point in time. And this K1 and the K2, in the case of a continuous time Markov chain, are positive reals that are the rates of an exponential distribution that determines how long you stay in each of those states. So what is the idea of a continuous time Markov chain? Suppose that we start our Markov chain with probability 1 in one state, and for that to be non-trivial, we start from state 1. The Markov chain tells you that it is a stochastic process such that you stay in state 1 for an amount of time that is exponentially distributed with a distribution that is equal, that has a parameter k1 plus k2. So if k1 and k2 are, usually those are rates. So the amount of time with which you stay on average here is 1 over k1 plus 1 over k2 time units. So you assume that you have an exponential distribution with this law, you sample from that exponential distribution, that gives you the sojourn time in that state, and then you jump to another state. And from here, you can jump either to 2 or to 3. The theory of Markov chains is telling you that you jump to state 2 after having waited for that amount of time with a probability which is equal to k1 divided by k1 plus k2. And you jump here with the other probability, k2 divided by k1 plus k2. That's essentially what a Markov process is. For simplicity here, I'm assuming that this is an absorbing Markov process with absorbing states, which means that once I hit those states, there is no outgoing transition, so I'm absorbed into these states. And the probability with which I'm absorbed here essentially will be proportional to these two rates. It is not important to fully understand what it is, because what it is important is that you can describe the dynamics of a continuous time Markov chain as a system of linear differential equations over variables that are the probabilities of being in each of the state at each point in time. And this is the dynamics of a Markov chain. So starting from some initial probability distribution, so values for pi1, pi2, and pi3, such that they are greater than 0 and sum up to 1, if I solve the system of differential equations, I get the probability distribution at all time points. Okay? So continuous time Markov chains are very, very popular in the field of computer science, in like quantitative methods for computer science, because they are a good abstraction for handling computer systems for which you have some notion of uncertainty. And the uncertainty here is the duration, for example, of the execution of a program. Somehow you interpret it as a Markov chain by giving it exponential distributions, and you can then analyze this Markov chain. You can do lots of things on top of this structure. But in many cases of Markov chain models, the number of states grows very large with the number of components that you are modeling. And that's what we call the state space explosion problem, which is also a very important problem also in other areas of in other disciplines, for example, for Markov digital processes and related techniques. So there has been a lot of work about trying to lump Markov chains. And this work actually goes back as far as the 60s with the first idea of lumping in the book of Kamenev-Snell about saying what it means to lump a Markov chain. And computer scientists have defined lots of algorithms in order to actually lump those Markov chains. So here, what you observe is that we can provide a lumped dynamics in terms of a forward equivalence, because if we can express x2 plus x3 trivially in terms of their sums, because x2 and x3 do not appear here because they are absorbed processes. They only take mass that is coming from state 1. So here is a lumped system of differential equations, which is equivalent in terms of forward lumping, because pi1 is the same as big pi1, is capital pi1 is equal to pi1 here, and capital pi2 is equal to the sum of the two. So if you're interested in the overall probability of getting absorbed, because that's what this pi2 gives you, you can use this model. And the important thing about Markov chain lumping is that the conditions, the criteria for lumping, are not specified at the level of differential equations, but they are specified at the level of a transition matrix, at the level of this discrete structure. And this is the condition for forward lumping. What it's telling you is that any two states, so if you get a partition of the state space of the Markov chain, it is called orderly lumpable, which has also been called forward lumping later on. If for any two states in each block, we have that these two states have an overall aggregate rate toward any other block of the system. I'm not going to go into details of that because we will pick it up from here to extend this idea to differential equations. But here the crucial point is that you don't look at continuous dynamics anymore. And this is a characterization of forward lumping. In order to find the forward lumping, you need just to essentially reason about a discrete structure. But that applies all in the case of a continuous time Markov chain, which in terms of a dynamical system is a very specific case of a linear system of differential equations. So here, essentially the condition that I was showing before reduces to checking that Q21 is equal to Q31, so there is no transition going from 2 to 1 and no transition going from 3 to 1, which implies pi2 of t equals to the sum of these two probabilities at all time points. And all our effort was to try to generalize the idea of lumping to nonlinear, in this case, polynomial system of differential equations, starting from these ideas. And in particular, what we need is somehow what I'm calling here the structural analogous to a transition matrix. So what the structural analogous for a nonlinear system of differential equation to this kind of structure which only makes sense for continuous time Markov chains. Okay? So now I'm telling you what this structural analogous is. And this structure is what we are calling a reaction network. How do we create this reaction network? We create in this way here. So this is a representative situation of some variable in a polynomial system of differential equations. You are defining the derivative of the kth variable. That is the sum of these monomials, where you have some coefficient alpha, and you have xi to the power of pi for all possible variables here. That's what you get. And we have system differential equation with lots of such monomials. We take each monomial individually, and for each of them we create this structure here. So this structure is if you're familiar with the chemical reaction networks, it's some kind of a chemical reaction network, because it is saying that on the left-hand side, you put P1 copies of x1, these are integer values, P1 copies of x1, P2 copies of x2, and so on and so forth. On the right-hand side of this reaction, you put the same plus xk, where xk is the variable that is increasing, that is changing somehow with respect to this monomial. And then you put the alpha here on top of that. So all of a sudden, this becomes completely discrete, because these are the variables xn, but in the definitions of forward lumping, we never talk about these variables. And these are integer values. This is a graph which takes multisets into multisets. So populations, vectors into vectors, parameterized with this alpha. If you think of if you're familiar with chemical reaction networks, it is like something like a chemical reaction network. But the chemical reaction network requires this alpha to be positive for that to have a physical meaning. This can be also negative. So formally, it is an extension of the chemical reaction network. But where things are called stoichiometric coefficients, so how many copies you need of a particular species in order for the reaction to take place, those are usually called species, because those are H2, O2, proteins or whatever, so they are these chemical species, and that's the reaction rate that gives you the speed. And I want to stress that this construction here has no physical meaning whatsoever in general. It's just used for the reasoning on this discrete structure, is to find the equivalences on this graph. That's a kind of a hypergraph, so it's not linking nodes to nodes, but sets to sets, multisets to multisets, and we want to find an equivalence here. Clear? So here is an intuition that I will come later to the formal definition that can be appreciated from people that are familiar with process algebra, which is a theoretical model of concurrency in systems. So probably you will not appreciate it. But essentially the idea is that we want to find equivalences over those species. And essentially what we say somehow informally is that we want to say that the species are equivalent when they somehow interact in equivalent ways with respect to their environment. And their environment is whatever is left here on the left-hand side of each reaction.
So are you describing right now roughly how an algorithm is created?
I am now describing what are the conditions on those graphs that characterize the notion of lumping at the level of differential equations. I will come back to this point in the next slide.
So will it be correct to say that you're now describing output specification of the algorithm?
Yes, I'm describing what are the conditions on the discrete structure on those reactions, such that if this condition holds, I can lump the respective differential equations, and vice versa. If I know that those differential equations are lumpable according to a forward or backward lumping, then the discrete structure must satisfy certain conditions. Okay. And I'm giving you this condition now. Okay? So the condition is the following. So every reaction will be in this form, where you have a multiset of reactants, and rho I is the multiplicity of species xi, and this is a multiset of products. Now, I'm defining a number of quantities, actually two quantities, which we call the Flux Net Stochiometry, which looks like this. It's a quantity that depends on a multiset and a species, a particular species of this multiset. And essentially, it's a projection of the net flux with which this variable here is involved in any possible reaction of my system. So I sum across all possible reactions, each of them being the specification of a monomial and differential equation. And then what I sum across is alpha, which is the rate of that action, multiplied by pi I, so how many things I see on the right-hand side of the species, minus rho I. Okay? So these are integers. This is a real number. All of that would be a real number. It's completely discrete. It doesn't have anything to do with differential equations at all. Okay? Let's keep this condition in mind. That's what I call the flux net stoichiometry. It's an ingredient for this thing here, which is called the forward rate. Now, it's not very important that we follow exactly what it means. I will try, first of all, let me try to give you the explanation of what I want to do with that. I want to capture the intuition that species are equivalent whenever they behave the same together with all possible partners in which they are involved in the set of chemical reactions. So, this is the candidate species that I would like to test for equivalence. This is some possible partner, and this is a possible group of other species. And I'm defining the forward rate in this way. It's the sum across all the members of this group, which will be a candidate block of equivalent variables. It's a sum across all of that of these flux net stoichiometries. And somehow, and this is the major actually result that we have, which was about trying to actually find the right definition of FR, like this. This is normalized with respect to this multinomial coefficient, which again, it's only talking about these integer values that are the multiplicities that appear in the product. Okay? So if you give me one species, which is a test equivalence, a candidate block of equivalent species, G, and a possible multiset of other partners, I can compute this thing. Again, completely discretely, because I'm assuming that I have a finite system of differential equations. So I have a finite number of monomials, and I can compute all of those things for each pair, for each species, and for each possible partner that is ever appearing in the set of reactions that are encoding my system of differential equations.
So, is it true that you here do not assume that your reactions are of the special form you introduced earlier?
No, it is true. It is true. This holds for any reaction. The special form of reaction is such that if I apply this technique to those reactions in that special form, then I can characterize the equivalence at the level of differential equations. But this holds for any specification in terms of a system of a set of reactions, so a set of as a reaction network.
Could you repeat again? So, what's the definition of equivalence? So
now it's coming. So this is the definition of the thing that has to be computed in order to test for an equivalence.
Okay.
The definition is this thing here. You say that a partition of species, which means a partition of variables, is a forward equivalence if taken any two blocks of this candidate partition, for any two species in one block, we have that these forward rates are equal for all possible multiset partners rho. For all possible ways in which xi and xj can never interact with all the other environments specified in the list of reactions.
Can I ask you whether in your sum, where if I need to write down the pi i's in G and the pi i's are multi-set of product, is that right?
So here you're summing across all the variables,
Right.
the species in the block G.
In the block G.
Yes.
Okay.
For each of them, you compute this Flux Net Stochiometry,
And
which
where-
will depend on some row, which is a multiset here.
And where does pi come in here?
Pi comes in the phi.
Oh, come in the phi.
Yeah, it's hidden in the phi.
Okay. Now, the pi i's, do they range or they're fixed? Pi I is fixed for every I?
Yes, given the reaction, pi I is the integer associated to the right-hand side of xi.
Okay. Is there any degree bounds on pi?
No,
I?
it can be of any degree.
Any degree.
Yeah. It's a polynomial system of arbitrary degree.
Even when you apply,
Sorry?
I mean, do you have a priori bound on the pi I?
No, you have that the computational complexity of the algorithm will be depending on the maximal degree.
Ah, oh,
But
okay.
it's
Okay.
just about the algorithm. This thing
Okay.
works for any arbitrary order. We're not
Right.
fixing any bounds.
All right.
So,
So it's a huge system if the degree is high.
Yeah, it can be. It actually grows. I'll come back to that later. But the algorithm grows polynomially with number of species, number of polynomials, and the maximal degree. So it's not too bad actually.
All right. Okay.
So I have a question about the definition. So when you say for all multiset partners, you mean for all multisets raw or for all multisets raw that occur in the graph?
For all multisets row. For all
Okay.
row. Yeah.
Okay.
Yeah.
Isn't it
Because for those that do not appear in the graph, that is equal to 0 essentially.
because
Yeah.
I see.
Because essentially this is
I
not
understand.
interacting, so it will come back to 0.
Is this a combinatorial problem?
Yes, the proof is based on combinatorial arguments. So this multinomial coefficient essentially is somehow informally. I have to say that the proof was not due to mine, but by strong collaborators on this subject. But essentially, it is about some renormalization condition to make the sum across this polynomial work. But it's definitely a combinatorial flavor. But just in the proof, because the algorithm is polynomial. So even if this can grow very large, we don't care because we compute it once and we store it. The algorithm itself is polynomial efficient.
What about the storage space then?
Sorry,
What about the storage?
storage is also polynomial.
It's also
Yeah, with different coefficients, of course, but it's polynomial in time and space. Okay. Okay, so this is, as I was saying, it's very important. It's a characterization result, which means that I give you a differential equation system. If I can find the equivalence in terms of sums, then equivalent variables must satisfy this property, and vice versa. Which means that now we're reducing the problem of computing this lumping. We are lifting or moving from a continuous world to a discrete world without losing anything. So the backward equivalence is probably running out of time. It's essentially the same style, but there is a twist because it is essentially computed with respect not to a multiset of partners, but a multiset of equivalent partners. So given a candidate equivalence on the species, we need to compute things on equivalent multisets. So if I have A that is equivalent to B, in this lifted equivalence, the set, the multiset A plus B plus C is equivalent to 2B plus C, because A is equivalent to B, so we don't distinguish in the sum. That's a small technical detail. Also to tell you that essentially the algorithm that we defined for the forward lumping, up to minor changes, can be applied to the
That's for all C?
this works for all M and for all H in the same style.
No, the last line, is it for all C or what?
For any C, yeah. They're saying that,
every C.
yeah, they're saying that if,
For every C this has.
yeah, this is an equivalence relation over multisets, so it's labeled by this multiset M. Given an equivalence AB, any multiset is equal to that up to the identity of equivalent species.
So it's a kind of a partition of the multiset.
Yes, partition of the multiset induced by the partition of elements.
By that is consistent with, let's say, addition. So to speak.
Exactly,
Okay.
exactly. And once again, this is a characterization result, which means that we don't lose anything in doing that. Okay, so now what we have been doing so far is essentially
So you're only capturing linearity
yes.
and not products or anything.
No, we cannot say that we have a reduced system where a variable y is equal to x times x1 times x2. This we don't do. Just linear aggregation in that sense. So what we have now, I'm just giving you the conditions for the equivalence, but I've not told you how to compute an equivalence. And we do that using a fantastic result from essentially the theory of computation, which is a partition refinement algorithm, which is also what we need in order to be able to preserve observables. And that's why we call it maximal aggregation. So these are the quantities that we have in mind, and forget about this line, but this line is to tell you that it sounds very familiar to other definitions of equivalence for completely different structures, which means that we can hope to be able to somehow adapt or build on other algorithms in order to define our own algorithms, which is what we did. And we do that using a partition refinement, which, as I said, it's a polynomial time and space complex in the number of species, monomials, and maximum degree. And that's essentially an extension of a partition refinement algorithm for continuous time Markov chains. The latest one being published in 2010 by Valmare Franceschini. So what is, let me see, okay. Sorry. I will show you what the algorithm does on a specific example, just to get the intuition of what it is doing. So, and this is a case actually that occurs very frequently in many biological systems. It's a very basic model of binding, unbinding between proteins to form complexes and so on. And essentially what we have is that we have a protein, A, that has two sites. And these sites are the sites that are such that they can bind, that allow the bounding with some other protein to form a complex. In this case, the other protein is B. And you can bind to protein A at one of the two sites if the site is phosphorylated, if it is active. Otherwise, the site is non-phosphorylated, and therefore you will not allow the bind. So the model that I'm showing here, just for simplicity, is that you can get phosphorylated on your own without the intervention of other species in your system. So if you have a protein with two unphosphorylated sites, you can become phosphorylated at the first site with some speed, K1. And of course, you can also become dephosphorylated, so you can do the reverse reaction where PU becomes UU. And now, here I am constructing a symmetry to give you the idea. The symmetry is that the rate at which either phosphorylation site becomes active is the same. And also, the rate at which either phosphorylation site becomes inactive is the same. And then I'm saying that when either of them is phosphorylated, I can bind to B. And once I have formed this complex, APUB, I can unbind it into APU plus B again, with rates that are symmetric with respect to the binding sites.
So what's the meaning of juxtaposition?
This is a new species. It's a new symbol.
A new symbol?
It's a new symbol.
There's no multiplication, right?
No, sorry. Yeah, good, thank you. This is a new symbol, which means the complex formed by A and B. For visual simplicity, not so simple, maybe. It's a new complex.
Right.
So now we have 1, 2, 3, 4, 5, and 6 variables. Because each of them can be interpreted as a chemical reaction network, therefore as a system of differential equations to which we can apply a clamping. Now, what is the partition refinement? The partition refinement is an algorithm that computes the largest equivalence, which is the coarsest refinement of a given initial partition species. Okay? So, the input to the algorithm is the reaction network and the initial partition. In this case, I'm giving the initial partition as the trivial singleton partition where all the species are hoped to be equivalent, because I'm putting all of them in the single block. But I could specify another initial partition where I'm leaving some of the variables on their own as singleton variables, singleton blocks. Since it is a partition refinement which iteratively refines the initial partition, those that are left on their own will never be put together with other variables because we are computing a refinement. So the observables, I can define the observables by just considering another initial partition which is not the trivial one. And they leave some of the variables on their own. Okay? This is how I can preserve all the observables that I want. So given that initial partition and the reaction network, I can apply an iterative algorithm, which is a fixed point algorithm, which computes the maximal refinement of the partition, which is an equivalence. So the current partition becomes, at the first iteration of the algorithm, becomes the initial set of splitters. So what is a splitter? A splitter is an element, a block of variables that may break some equivalences that I'm testing. So here I'm hoping to say everything is equivalent, so I can put everything together. Now I apply the FR condition. I compute the FR condition for every variable and for every possible multiset of partners of my reaction network. Here I'm showing just the non-zero values, which means that all the other partners and variables that are not shown here are such that FR is equal to 0. Okay? So what I'm discovering with this first iteration is that PUB, this complex, cannot be equal to B because 4 is different than -3. Whereas in the definition of the forward equivalence, we had that for any pair of equivalent species, yeah.
How is the function FR given?
The function of FR was the function that we had before. Let me go back.
I know, but how do you input it? What is?
I compute it. I just compute it.
No, what is the definition of it?
This one. This one.
Yeah.
This is how I compute it.
Oh,
Yeah, that one.
okay. The forward.
This is the FR.
Forward rate.
So I compute all of them. I can compute them. The forward rate. Huh?
Okay.
So, and I can do the same with the backward rate, right? It's the same. But essentially I compute that, and I discover that there are things that are not equivalent, which means that this will be a splitter that will split this partition in things that cannot be further split by looking at all this list of FR computations that I made. So what this is causing will be as follows. So these computations here will not detect a non-equivalence, a difference between APU and AUP, because with respect to all the other partners, this is always equal. So it's 0 everywhere else, and 4 in the case where I'm computing this with respect to the empty multiset. So these are equivalent. These are also equivalent for the same reason. With respect to B, this value is -3 for some choice of K1, K2, K3, and 4, which I think it's 1, 2, 3, and 4 actually. And I'm also splitting B with respect to the rest of the system because B, let's say B, so B in this case it seems like that it could be put together with PU, but the forward rate of B with respect to itself is going to be 0, and the forward rate of APU with respect to B is -3. So B cannot be on its own, and B will be different. So at the end, in the next iteration, I've removed the set of splitters because I've computed them all, but I've introduced the new splitters. And these new splitters are AUU on its own, B, APUB, and AUPB. This splitter here would also have this thing here. But then we use another result from the partition refinement algorithm saying that we don't need to examine all the splitters that we generated, but we can remove the largest block. So at every iteration, we can remove the largest block from the current set of splitters, because the largest block, the result of the largest block is implied by checking it for all the other splitters. That gives us a strong reduction in the number of splitters that we compute at each iteration. Now, when we check the same things for all the other splitters here, we see that none of them will identify a difference between this candidate partition here, which means that at the end of the 4 iterations where we check first this splitter, then that, and then that, we have not discovered any difference whatsoever, but we arrived at a fixed point where now the set of splitters is empty, and there is nothing else to check, which allows us to conclude that this is the largest equivalence that refines the initial partition of species. And actually this makes sense because essentially it is discovering somehow the symmetry. It is telling you that in the model, PU and UP are the same because all the rates are equivalent, which is what we wanted to get by construction. Okay?
So in doing this computation, are the KIs fixed constants that you input?
Yes. There will be a follow-up question. What if KIs are unknown?
Right.
Excellent question, we don't know. We're trying to work on that because that would be the natural evolution of the work.
Right.
Would be what if, in particular in some applications like in biology, what if I don't exactly know the rate, or the rate is known up to some perturbation, or it's uncertain in an interval? What can we do about that?
So all these computations are these parameter dependent.
Yes, yes, indeed. We have some work that essentially uses some other techniques, solution techniques, which are not discrete anymore, but based on satisfiability modulo theory, so SAT solving, which allow us to say something independently of the parameters. And for some specific classes of networks, we actually have some proofs that tell us that if an equivalence holds when all the parameters are equal to 1, then it holds for any possible choice of parameters. But those results apply to specific cases. In general, this is what we have at the moment, that everything is known, all the interactions are known, and all the rates are known, such that we can actually compute numbers. Otherwise, we're essentially constructing a system of constraints.
So right now you are using whole integers as the computer. Obviously, that's not true because your rates are not integers.
No, integer is the degree of the polynomial. So that's integer.
The what?
The degree of the polynomial.
What is the degree?
The degree of the polynomial. So these are 3.0. And just these are numbers. And these are the rates.
So
those are positive.
So the
these are
four
reals.
rate calculation are integers.
The rates here are positive reals.
Positive.
They are reals in general.
Real. But what about the FRs? Why are they always integers?
Because I chose rates that are 1, 2, 3, and 4. So all these computations become integer state.
See, my question is then, how do you check -3 with another -3 when they're both real? No, you're not computing exactly.
That's a very good question. Again, we don't know. What we do is that we are using double precision computation in all the cases. And we assume that they are equal. We assume that when that tells us that they are equal, then they are actually equal. But of course, the numerical precision is a problem.
Machine equal.
Yeah, machine equal, yes. The numerical precision is a problem. The theorem works for the reals, but the algorithm works on a computer which is fine precision, so we have to accept that result. You can check that equivalence afterwards using symbolic techniques.
Okay.
If it is truly a reduction. But you don't have the polynomial complexity then, you have an exponential complexity.
Okay.
But you can check for consistency if you're really concerned about the precision of the equivalence that you get. Okay. And of course, we also have an implementation because we are computer scientists, and it is a polynomial. It is a polynomial algorithm. So in practice, it scales very well. So in an ordinary laptop, you can analyze systems with 2.5 million variables and over 5 million reactions, which means 5 million polynomials scattered throughout the system in about 5 minutes. Okay.
This is very impressive.
Yeah, because it's because under the assumption that all the parameters are known and you have polynomial.
Numerical and linear computations are fast.
Yeah, the computations are fast, and the algorithm is polynomial. That's the important part.
But like when you run this for 2.5 million, so how many variables do you get in the end?
It depends on the model.
But are you talking now
What
about
kind of
some
percent?
specific?
Okay, no, that's a good point. So what happens in practice, I don't have the graphs here right now, but what happens is that the cost of the time of the reduction is largely to how much you can reduce. Why is that? It seems counterintuitive, but it's not so counterintuitive. So if you aggregate a lot, if your model is very much reducible, it means that you need fewer iterations, because you start with a very coarse partition and you refine very few times. And therefore, you stop earlier. And so you are fast, because you reduce a lot. If you don't reduce a lot, since you always discard the largest block of splitters, you have a logarithmic decrease in the number of variables that you're checking in every iteration. And that compensates the fact that you need far more iterations. So overall, if we did it on synthetic benchmarks, if you gave the same system with an increasing reduction possibility, the time span between the maximal, the system that can be aggregated a lot and the system that cannot be aggregated at all is about 200%. So one is two times faster or slower than the other. But you can reduce from 2.5 to 200 and 2.5 to 2.5, so you don't reduce at all. So the orders of magnitude of reduction is much larger compared to the orders of magnitude in difference in between the runtimes.
Is the maximal partition reduction unique theoretically, and would it turn out practically unique?
It is unique. Yes, it is unique. You can prove that this is why it is unique. Assume that there are two equivalences, then you know that the union of the two, the transitive closure of the union, is also an equivalence. So there is always a one.
Okay, that's the theoretical one.
Yeah. So it is always unique.
What about the practical one?
In practice, then of course you get up to the machine precision, you get also the same result.
You sure?
Yeah. If you assume that the machine precision is not a problem, then this one will give you the maximal aggregation.
So you're saying that the algorithm provides a path to give you
The largest equivalence.
the largest thing, and no matter what algorithm you use, you're going to get the same.
Well, in our implementation, of course, because we are not assuming that the implementation of our algorithm is correct. And in which case, in which case, you're going to get the only one that exists.
Right. Okay. But so you prove that there is a unique one. So and you said that you have to use symbolic computation to check that that's really the correct answer, because you don't know whether the algorithm is implemented.
No, of course we did some tests, and the tests are pretty comforting that reduction. We don't double check with symbolic computations. I'm telling you that you could do it if you want. You could do it if you want, but we don't do it. It's not in our workflow, but it's
Do you
possible.
actually use it to solve real problems?
Yeah, sure, of course. So these are some results from benchmark models in the literature, which are computational models that have been studied in a number of papers from other.
Are they artificial models or?
No, they are models that are, some of them are, so this is artificial, it's a test.
Okay.
But all of them are models that have been validated against experiments in the lab. These are from biochemical reaction networks. This is, I think, it's an affine model coming from weather modeling. So this was a kind of a synthetic benchmark for a technique published in this paper. What I'm showing is that it is designed to be aggressively reducible with the number of variables 222 as opposed to 262,000. And I'm showing you that the forward and backward are pretty much comparable in terms of time. There is only one difference because you have to compute that multi-set equivalence that somehow slows down the backward a little bit. And this is a case where backward and forward coincide. This is a case where backward and forward do not coincide because that's the maximal aggregated forward reduction. This is the maximal aggregated backward reduction. In this case, that aggregates more, but there is also the side condition that equivalent variables have the same initial conditions. And Yeah.
can you iterate
Yes.
forward, backward, forward,
Good,
backward?
good
and then
question.
the other
Because I
one?
prepared that for a mathematician's audience. So now let me use it. Excellent question. I was almost forgetting about it actually. So this is quite funny actually. You can iterate. I don't know where you can end. I don't have any clue about if there is a fixed point, if it depends on the order with which you apply things. This I don't know.
Look, if you do a forward and you said that the maximal partition is unique, and then you do a backward, then I suppose that's also unique. Then now when you go take the forward on the backward,
Counterexample.
you know what I'm asking, right?
I'm asking, yeah. So this is the maximally aggregated forward. I take that as an input. I'm just replacing y with x.
Right.
This is now the original system of the backward, and this is the maximal backward. But then, that also enjoys a forward, because y1 plus y2 is equal to 0.
Right.
So here I'm losing all of the dynamics, but it is an aggregatable model. And you cannot aggregate further than that because you only have one variable, which is equal to 0. The thing is that when I apply this chain of equivalences, I'm also introducing side conditions. Namely, that all the variables that are backward must be initialized with the same initial conditions.
Right.
So I don't know, it's unclear, and we have not investigated it a lot, whether what is the interplay due to this introduction of side conditions.
If I understand you're saying, is that so you have a forward and a backward and a forward, and you get that, you get
Zero.
nothing.
Yes, because under the assumption that things that are backward are initialized with 0, and you don't care about the sum of solutions,
Right.
you lose everything. But that's a specific case that was
Right.
done on purpose
Right,
for the talk. It's not something that you find in general. In general, you don't aggregate. We tried to apply it to some models from the literature, and benchmark models, and we didn't find many more reductions after a second cycle of application of the forward and or the backward in practice. But in theory, it is possible.
But in theory, if you take a forward and backward and forward, you should get the same forward result, right? Same,
No.
You said there's a unique maximum. Oh, from every input.
Exactly.
So after you change it, then your uniqueness is gone.
Yes.
So is the uniqueness due to the algorithm or not?
The uniqueness is due to the. I think the uniqueness is due to the essential linearity of the dynamics that you find. You can think about. Essentially, the uniqueness is due to the fact that if you have two different equivalences, then the union, the transit closure of the union is also an equivalence, and therefore you get equivalence.
That's for the same system.
For the
For
same system.
given system.
Yeah.
But once you transform into the forward one,
Yeah.
it's a different system in some sense.
Yeah.
I mean, at least in terms of its later maximal partition, right? So what I'm saying is that, so you have a system, you said that there is a unique forward maximal partition.
Yeah.
You get the forward maximum partition.
Yeah.
And then you apply a backward and then some other forward.
Yeah.
And
Or if you end up with the same maximal forward, depending on the order.
so what kind of equivalence? If you can actually get a different partition because of that iteration, then how are the system equivalent?
The point is that if you introduce the side conditions or the initial conditions due to backward in the loop, this is not clear whether
Maybe
that will
they were never consistent.
They will exactly
Uh-huh.
exactly in that
So
case.
you actually cannot.
Yeah,
Okay.
they might introduce to different partitions because of the side conditions that you are imposing.
Can I ask you another question?
Yeah.
When you talk about maximal partition, right, reduction, in what order are you ordering the partitions?
Whatever order. I don't need an order for the partitions.
Well, then what does maximum mean?
Maximum means the coarsest.
The what?
The coarsest. The coarsest partition. The partition with the fewest number of
Right.
blocks.
And that's unique.
That is unique.
Okay, thanks.
I think that we are well beyond the given assigned time slot, so I think let me just wrap up. Okay. So here are some examples taken from the literature about what we can discover about them. We can talk about them offline, but in practice you can discover reductions that make sense also from a physical interpretation point of view. You can apply it to many different kinds of systems. And that's it. Essentially what we have is an algorithm for exact reductions. We are looking at reducing things that are approximately equivalent when they are somehow variables have derivatives that are equal up to some perturbation of their parameters. Like K1 and K1 prime, they're not exactly the same in the previous case, but it's an epsilon distance from K1. And we can think about them. We have a recent paper, we're working on that. It's fresh, and we don't have many clear results, clear ideas about how to move it forward to approximate somehow perturbations, it's therefore approximate reductions. We are looking at differential algebraic equations, to come back to your problem, where we introduce also some constraints on the variables. And this paper we are presenting next week in Miami. At the moment it works for linear differential algebraic equations. And we hope to extend it somehow to non-linear case as well. And we're also looking at new applications in areas where the derivatives are, there's some kind of structure that we hope to exploit in our algorithms, like in brain network models and the models from electrical engineering, but it's something that is still really kind of future work that we are only kind of barely touched until now. That's it. So these are my collaborators, and that's all. Thank you very much for listening.
More questions?
Is your, from your system to the partition system, is there any analogy to something like the prime decomposition of a system?
What decomposition?
Prime decomposition.
Yeah, prime.
Well,
No, you have a system which need not be prime. In terms of the ideal.
Ah, yeah. So, yeah. So, good question. I think that this series also had Andre Platzer as a speaker at some point.
Yes.
So he's working on that in that area for finding invariants. There is also a colleague of us in Florence that's working in similar areas, using those ideas to do reductions. I'm not really an expert because I don't know those works very well to be able to give you an answer with 100% certainty. What I can tell you is that from my understanding, there are algorithms that look at similar ways of reducing, but those algorithms, being based on a Gröbner basis, they are doubly exponential.
Right, yeah.
And in this case, we are still in the polynomial realm of computational complexity. And also,
his ideal is prime.
Hmm?
His ideals are prime. Prime differential ideals.
Yeah.
The ideals given by
Yes.
those systems, they are prime differential ideals. You can, like, it's an exercise to prove it.
When you're in dynamical form, yeah.
Yes.
Yes.
Yeah, right.
They're prime.
But,
If you do
but
algebraic
when you
differential,
want to talk about differential algebraic systems, then
Yeah, then it's a different story.
different, right?
it's a different story. But those are prime. The ones
Those
that
are prime,
we
okay.
talked about.
Thanks.
there is some
Some
work.
technical notion, prime ideal.
Yeah, I know. There is some work that essentially has been appeared either in Foxx 2017 or 16 using algebraic techniques. And then I need also discussion with the author. It seems that the assumptions are different because those reductions can be applied, for example, the forward analogous of that can be applied for a specific initial condition. Whereas here, we are independent from the initial condition for the forward case. So therefore, the two techniques are not comparable because the assumptions you're making,
They're independent.
they are independent.
But the equivalents are not independent of the initial condition?
No, but what I'm telling you for the forward condition, for the forward equivalence, that this holds for any initial condition on the original system, so long as you initialize the reduced system appropriately, consistently.
Okay.
Whereas the other works that I was mentioning, instead, I think that they apply a reduction assuming a specific initial condition. And if you fix a specific initial condition, you may reduce differently. In particular, you may reduce more. But of course, you are constraining the reduction more because you are also, you cannot compute anything for a different initial condition.
That's all?
So the forward rates are invariant, right?
Invariant with respect to?
With respect to your equivalence, I suppose.
What do you mean by invariant in this?
Well, I mean, you said that if they have the same value when you computed it, then you put it into the same partition.
Yeah, yeah.
So that.
Yeah, they are invariant. Yeah. That's
That's
yes,
there.
yes.
Okay, so that's it. Thank you.
Thank you very much.